Hello and welcome to the first of two lectures on pre-calculus that we're going to need for our calculus course. In these two lectures, we're going to look at some algebra and trigonometric ideas and refresh our memories of some pre-calculus. In particular today, we're going to look at some graphs of equations and some properties of graphs like symmetry and intercepts. We'll see an example of how equations can be used to model some real-life problems. And near the end, we'll look at functions, one of the most important ideas in all of mathematics. Hopefully, most of this will seem like a review, but if you're like me, you might have forgotten a lot of this. And one of my goals in all the lectures is to remind ourselves of where pre-calculus plays a key role in calculus. So let's first talk about how you sketched the graph of an equation. And I'd like to look at a particular example to show you some graphing techniques. Let's look at the equation y equals x squared minus 2. And one way to start getting a feel for what the graph looks like is point plotting, meaning you take certain values of x, you plug them into the equation, and that generates a y value, and you fill out a table of values for x and y. For instance, if x is minus 2, then the y value corresponding to minus 2 would be minus 2 squared minus 2, which of course is 2. And you fill out the table of values as I've shown here, and then you can plot those points in your xy coordinate system, and you'll see that they seem to form some kind of parabolic shaped curve. Now, of course, if you join the points, it's not really clear that it would be a parabola here. It would be that curve that I've drawn. And in fact, one of the goals of calculus is to make sure that by point plotting, you get the right curve. So let's step back about point plotting. In particular, you need a lot of points to get a good graph. I just did 5 or 6 points there, and the graph might have looked completely different. Point plotting, actually, it's kind of interesting, that's how graphing calculators work. If you feed in an equation into a graphing calculator, it just plots the points and then connects them with a curve. In calculus, in this course, we will learn much more advanced techniques for plotting graphing equations, and these calculus techniques will use what we call the derivative. One of the most important ideas of a graph, or one of the most important concepts to understand about a graph, is that of its intercepts. Where does the graph cross the x-axis, and where does the graph cross the y-axis? Again, let's look at an example. Let's consider y equals x cubed minus 4x. Let's find out where this graph crosses the axes. Well, to find the x-intercepts, that's where it crosses the x-axis, and that would be where y is equal to 0. So take our equation, let y equal 0, and solve for x. So we would get x cubed minus 4x, we factor it into x times x minus 2 times x plus 2, and set that equal to 0. And we determine that there are 3 values of x that make that equation true. X equals 0, 2, and minus 2, which gives rise to 3 x-intercepts, 0, 0, 2, 0, and minus 2, 0. So the graph touches the x-axis 3 times. The y-intercepts you get by letting x equal 0, and the only y-intercept then is 0, 0. Here's a picture of that graph, and you can see how it touches the x-axis 3 times and the y-axis once, in fact, at the origin. Those are the intercepts of that equation. Another important idea of graphs is that of symmetry, and we'll be using symmetry quite a bit in this calculus course. We say that a graph is symmetric with respect to the y-axis if whenever a point xy is on the curve, then so is the mirror image point minus xy. So this curve or this equation would be symmetric with respect to the y-axis. Now there's symmetry with respect to the x-axis, and it's very similar. If a point xy is on the curve, then so is the point x minus y. And finally, there's the idea of symmetric with respect to the origin. And in this case, we say that a graph is symmetric with respect to the origin if whenever xy is on the curve, then so is the point minus x minus y, which is on the line that passes through the origin. Good. Let's look at an example of a problem involving symmetry. Let's consider our curve that we looked at earlier, y equals x cubed minus 4x. What kind of symmetry does the graph of this equation possess? Well, you might remember the graphs seem to be symmetric with respect to the origin. Let's now verify this algebraically. And the way you do this is you take the equation y equals x cubed minus 4x and you replace x with minus x and y with minus y and see if that gives rise to the same equation. So watch the algebra here. I take the equation and instead of y I put in minus y and instead of x I put in minus x. So I get minus y equals minus x cubed minus 4 times minus x. A lot of minus signs if you ask me. And then I can do some arithmetic here. I get minus the quantity x cubed minus 4x, and then the minus signs can cancel, and I'm left with the original equation, y equals x cubed minus 4x. In other words, if xy is on that curve, then so is minus x minus y. And as you see, that curve is symmetric with respect to the origin. Good. Let's now talk about points of intersection of equations, of graphs of equations. And again, I'd like to do an example to illustrate this pre-calculus topic. So let's look at a couple of equations. The first one will be x squared minus y equals 3, and the second one is x minus y equals 1. You might remember that that first equation is actually the equation of a parabola, and the second equation is that of a straight line. And we're finding where that parabola and that straight line touch each other. So, how do we do that? Well, the first thing I'm going to do is take the equation of the parabola and simplify it to be y equals x squared minus 3, and for the line, write it in a different form, y equals x minus 1. So what I've done here is I've taken the original equations and written each equation as a relation y equals in terms of x. And now I can set those two equal to each other, and I get x squared minus 3 equals x minus 1. Bring everybody over to the left-hand side, x squared minus x minus 2 is 0, and factor. There's a pre-calculus skill, isn't it? We have to be able to factor polynomials. This factors quite easily. X minus 2 times x plus 1 equals 0, and hence x is either 2 or minus 1. And so knowing when x is 2, you can plug that back into either equation and get that y is 1. And when x is minus 1, you can plug it back into either equation and get the y value to be minus 2. Here's a picture of our situation here. We have the line and then the parabola, and notice that they intersect twice. The point minus 1, minus 2, and the point 2, 1. Later on in this course, we'll be able to use calculus to calculate the area bounded by those two equations. That's kind of an odd-looking region, and yet calculus will give us the skills to calculate the area. I suggest also that you use a graphing calculator to verify the results. In other words, for yourself, draw that graph of the two equations, and you'll see that they do intersect at the 2 points. Remember, graphing calculators are required for the advanced placement exam. They aren't optional, they're required for the AP exam. So as we go through this calculus course, I highly suggest you become familiar with your graphing calculator and use it to verify a lot of the results that we do. That said, it's kind of interesting that there's quite a controversy about the usage of graphing calculators at the university level. Many of my colleagues don't like graphing calculators and don't allow them in the classroom. Personally, I love them, and I use them all the time when I teach mathematics. But it is interesting that there's still a lot of discussion on whether or not it's a useful tool or not. I really think it's useful, but you can make mistakes with the graphing calculator. It can mess up a little bit, and we'll see some examples of that later on in this calculus course. Now, another concept that's crucial for understanding calculus is that of a straight line. Now, we've looked at lines earlier already, but let me be more specific now about some of the ideas involved with lines. First of all, there's slope, and we used slope in the previous lecture. Remember that the slope of a non-vertical line passing through a couple of points, x1, y1, and x2, y2, is equal to the change in y over the change in x. And they often use this notation delta y over delta x. That's a Greek letter delta, and it stands for change in y over change in x. So it's y2 minus y1 over x2 minus x1. And of course, I said the line was non-vertical. That's equivalent to saying that x1 and x2 were different. Otherwise, you'd be dividing by 0, which is a no-no in mathematics. And by the way, the order of subtraction is important here. If you're going to use y2 minus y1 in the numerator, make sure you use x2 minus x1 in the denominator, not the other way around. Here's a picture showing our 2 points, x1, y1, and x2, y2. And I've drawn the line, the vertical line, and the horizontal line, which reflects the idea of change in y, the vertical distance, divided by change in x. Let's do a particular example. Let's find the slope and the equation of the line passing through 2 points. How about the points 1, minus 1, and 4, 1? So remember, slope, and we use the letter m for to denote slope. It's the change in y over the change in x, so it's 1 minus minus 1. That's the change in the y values, and the change in the x values is 4 minus 1. We simplify this, we get 2/3. So the slope is 2/3 of this line, and we can now find the equation of this line having slope 2/3 and passing through the point 4, 1. We'll use something called the point-slope form. We used this in the previous lecture. And the way this formula works, it's y minus 1, that 1 being the y-coordinate of the point, equals the slope, 2/3, times the quantity x minus 4, 4 being the x-coordinate of that point. And then you simplify that to y equals 2/3 x minus 5/3. That's called the slope-intercept form of a line. It's really a neat equation because it shows you the slope, that's the number in front of the x, and it shows you the y-intercept. In other words, when x is 0, y is minus 5/3. And sometimes people don't like fractions, so they multiply through the equation and get a more general form, 3y minus 2x plus 5 is 0. That's not as useful, I don't think. Nor is it unique. You could multiply that form by 6 and get a different general form equivalent to the original. So here's a picture of our line through the 2 points, 1 minus 1 and 4, 1. The slope was 2/3, which means it's rising. It's going upwards as you go left to right. Let me step back and talk about something that is often confusing to students, and that is the issue of horizontal and vertical lines. Remember that horizontal lines, like the x-axis is a horizontal line, they have slope of 0. The rise over the run is 0. There's no rise at all. So horizontal lines have slope 0. For vertical lines, slope is not even defined. Okay? It's not even defined. Vertical lines do not have a slope. And then, perhaps most important, please memorize the equation of a line of given slope m passing through the point x1, y1. That equation, the point slope formula, is y minus y1 equals slope m times x minus x1. Again, that formula will be used over and over again in this course. So, let's talk a bit about parallel lines, and then a little bit later on perpendicular lines, and do some examples. Let's find the equation of a line passing through the point 2 minus 1 and parallel to a given line. The given line being 3y minus 2x plus 5 equals 0. So I'm given a line, and I'm given a point, and I want to find the line through that point parallel to my given line. Well, let's see how to do it. The given line was 3y minus 2x plus 5 equals 0, and I can rewrite that into slope-intercept form by doing some algebra, and I get that the equation of the line is y equals 2/3 x minus 5/3. So the slope of that line is 2/3. So the parallel line will have the same slope 2/3, but pass through the point 2 minus 1. So I just plug that into the formula. Y minus a minus 1 is 2/3 x minus 2. I'm using the point slope formula here. I then simplify the algebra, and I get the line y equals 2/3 x minus 7/3. Now let's talk about that line. Its slope is the same as the original line, 2/3, but it passes through the point 2 minus 1. You can check that by just plugging in 2 and minus 1, and it satisfies the equation. Cool, we got that. Let's do a little bit harder problem. Let's find now the equation of the line perpendicular to our given line, 3y minus 2x plus 5 equals 0, but again passing through the point 2 minus 1. So I don't want the parallel line now, I want the perpendicular line. Well, what's the relationship between the slope of a line and the slope of a line perpendicular to the given line? And you might remember that the slopes are related in the following way. The perpendicular line has slope negative reciprocal of the original slope. So let's solve this problem. The slope of the original line, as we saw earlier, was 2/3. So the slope of the perpendicular line is going to be the negative reciprocal. The reciprocal of 2/3 is 3/2, and then the negative in front. So the perpendicular line has a slope of minus 3/2. And it passes through the point 2 minus 1, so we use that same formula. Y minus a minus 1 equals our new slope, minus 3/2 times x minus 2, and then we simplify and we have our answer. Well, let's look at a picture of all this. We can now graph the original line, and then that parallel line, and then the perpendicular line. I suggest you do this with your graphing calculator, with your graphing utility, to verify your results. The three lines are y equals 2/3 x minus 5/3. That was the original line. The parallel line was 2/3 x minus 7/3. And the perpendicular line was minus 3/2 x plus 2. Your picture on your graphing utility should look something like the picture here. A hint here, make sure you use a square setting when you graph this. so that the perpendicularity is achieved. So let me draw some conclusions about straight lines. The slope-intercept form of a line is y equals mx plus b. M is the slope here, and b is the y-intercept. Horizontal lines have equations y equal a constant, like y equals b. Vertical lines, going up and down, cannot be written in point-slope form. They cannot be written in point-slope form. Why not? Because they don't have a slope. Slope's not defined. But you can find an equation for a vertical line passing through C by just using the equation x equals c. Here's an example of two lines, one being horizontal and one being vertical. I've written here, or shown here, the line y equals -3. That's a horizontal line. And then the line x equals 5, that's a vertical line. Now, one of the big applications of mathematics is modeling real-life situations. Let me show you a very simple example of a mathematical model that I think you'll find quite interesting and quite useful. You probably realize there are two sets of temperatures that people use, the Fahrenheit and the Celsius scales, and we're going to find a formula that relates those two temperature scales. So in particular, we're going to find a linear equation that expresses the relationship between the temperature in degrees Celsius, which I'll call C, and degrees Fahrenheit, F. And to do this, we're going to use the fact that water freezes at 0 degrees centigrade, which is equivalent to 32 degrees Fahrenheit, and then it boils at 100 degrees centigrade, which is 212 degrees Fahrenheit. So let's get to work. Let's find the slope joining those 2 points, the points being 0, 32 and 100, 212. So slope is change in the y values. Well, the y is now the F values, the Fahrenheit values, over the change in the x values, which are now the centigrade values. So it's 212 minus 32 over 100 minus 0. And if you simplify that, you get that the slope is 9/5. Good. And now we know the slope. We can pick either of the points. How about the point 0, 32, and we plug that into the point slope equation to get f minus 32 is 9/5 c minus 0, and then simplify that to get Fahrenheit equals 9/5 c plus 32. So that's a formula, an equation that relates the Fahrenheit temperature to the centigrade temperature. And by the way, I think you could see that you could manipulate that equation a little bit and get another one that is of the form C equals something with Fahrenheit. That wouldn't be hard to do. So how could you use this equation? Suppose you're traveling in Europe and you read the newspaper and it says tomorrow's temperature is going to be 30 degrees centigrade. And you go, well, I don't know what that means. Well, with this formula, you can figure out the corresponding Fahrenheit temperature by plugging 30 into the equation. And if you do that, you get that F equals 9/5 times 30 plus 32, which is 86 degrees Fahrenheit. And you'll say, well, I better wear a t-shirt today. It's going to be pretty hot in Europe. Good. Let me now talk about briefly the idea of function. We'll continue this discussion in our next pre-calculus review lecture next time. But let me just remind ourselves about what functions are. Let's look back at that equation y equals x cubed minus 4x. This can be thought of as a function from the set of real numbers to the set of real numbers, in the sense as follows. Every time you pick an x value, a real number x, you plug it into that equation, and out comes a y value, a unique y value, which is often called f of x. It's the image of that particular x value. I'm not exaggerating when I say that the idea of a function is perhaps the most important concept in all of mathematics. The use of functions permeates all of mathematics. This word was first used historically by Leibniz in 1694, but it's clearly an older idea. Even in 12th century Persia, they were dealing with the idea of a function. Let's be more specific now. Here's a more technical definition of a function. Let A and B be two sets of real numbers. A function from A to B is a correspondence that assigns to each element x in A unique value y in the set B. The set A is called the domain of the function, and the image of x in the set B is called the image, and the range of your function is the set of all the images. So those are some technical terms about functions that you can read about in any pre-calculus textbook. Let's do a couple of examples. We've seen this function before. It was f of x equals x squared, our parabola. And this is a function whose domain is all real numbers. You're allowed to plug in any x value you want into this function, and out comes the square of that x value. And you notice that the values that come out are never negative. In fact, the range would be all non-negative real numbers. This is an example of a function that I carry in my back pocket. By that I mean we use this function so much in calculus that I just have it right back here because it's something I'm going to need over and over again in my calculus class. Here's a graph of x squared. We've seen this graph before, and it's very familiar to us as a parabola. Here's another nice looking function, f of x equals the square root of x. Well, now the domain's a little limited. You can't take the square root of a negative number in elementary calculus. If you try to do that on your calculator, you'll probably get an error message. So the domain here is the interval 0 to infinity, and that includes 0, and the range is the same from 0 to infinity. Notice that it kind of begins at the origin 0, 0 and goes off to the right. So we've now finished our first of two review lectures of algebra and what I like to call pre-calculus. Next time we'll talk more about functions. I'll give you more examples of functions that will play a major role in our calculus class, and in particular we'll spend quite a bit of time on trigonometry. Let's look at an example now that puts a lot of these ideas together. Consider the equation x equals y squared minus 9. Let's talk about features of this equation. For example, what are its intercepts? Well, I think you can see that if y is 0, then x is minus 9. And if x is 0, then y is 3 and minus 3. So there are 3 intercepts. What about symmetry? I think you see that if you replace y with negative y, you get the same equation back. So this is symmetric with respect to the x-axis. Now, most important, is this a function? Is this equation a function? And I hope you see that it's not a function. Well, why not? Because for a given x value, there can be more than one y value that corresponds to it. So this is not a function of x. For example, x equals 0 corresponds to both y equals 3 and minus 3. Here's a picture of that equation. And notice that vertical lines would hit that equation possibly more than once. And that's one of the geometrical indications that a graph is not the graph of a function. Because a vertical line hits it twice means that for a given x value, there are more than one y values. So we've pretty much finished our first of two lectures on pre-calculus. Next time we'll talk a lot more about functions, and in particular, I'll spend quite a bit of time reviewing trigonometry. And again, I'll point out lots of instances where pre-calculus plays such an important role in calculus. Thank you very much, and see you next time.